So I've got two more complicated, juicy points to discuss. And the first one is about the fact that this thing that we've found doesn't just work as a left inverse, it would also work as a right inverse. So one way that you could verify this is just by taking this, putting it on the right of this matrix, multiplying the two of them together, and you would find that it gives you the identity matrix. It does work, therefore, as a right inverse. This result that we found as a left inverse, it works also as a right inverse. But I want to actually show you something more interesting, which is demonstrate how this same approach of Gaussian elimination, we could have done it with matrices on the right rather than on the left. And there it would involve us doing Gaussian elimination on the rows, sorry, not the rows, the columns rather than the rows, which is just less conventional. It's less easy on the eye. You have to think slightly more, concentrate, because you're less used to doing it that way. And I would advise that you always do it on the left because you're less likely to make a mistake because you're just more used to doing that. But I want to demonstrate that you could do it on the right and get to the same answer. So we'll just take the simple example in this case, so the case where a is not equal to 0, and you can do the same example that we've just done where a is equal to 0 on the right as well, but I won't do that for you. I'm just going to take the simple example just to illustrate that you could do this on the right just as effectively as on the left. So here is our matrix again, A, B, C, D. And now what we're going to do is put a matrix here and multiply the two together, and we're trying to get our answer closer to the identity again in this Gaussian elimination fashion. Now, in this case, what we're going to put in this row here, so column, everything that was in terms of rows now is going to be in terms of columns. So what we're going to put in this first column here is going to determine what we get in the first column here. And the entry here is going to be multiplied by this column, and the entry here is going to be multiplied by this column, and then you're going to add the corresponding bits together to get what goes into this column here. So our first maneuver is to try and get this thing again to equal 1. So we're going to therefore multiply that first column by 1 over a, and as I said, we're taking the simple example where a doesn't equal 0. I'm not going to consider the example where a equals 0. You can do that for yourself. It's just like what we've just done in the left row case, but now in terms of columns. I'm just doing the simple case just to demonstrate that you can do this in terms of columns. And then we're going to take 0 lots of the second column, because all we want to do is multiply that column by 1 over a. We don't need any amounts of this second column here. So 1 over a, 0, and what that is going to give us is going to give us 1 there, and then it will give us c over a here, because we've taken no lots of that column. Just to confirm it in the full lengthy way of matrix multiplication, you take a times 1 over a, which will give us 1, and then b times 0, so we get 1, c over a, d times 0, so no contribution there. So that's what we get in those two entries there. Now let's think about what we're going to do with the second column here. So we would like to make this entry here now equal to 0. So to do that, we need to take away a multiple of this first column here, and that multiple we're going to need is going to be minus b over a, I think. Let me just check. So if we multiply this column by this, we'll get the a will cancel with the 1 over a, and we'll get just minus b, and then we'll take that there. So that'll be excellent. And then we'll have 1 here. So that takes minus b over a lots of this column and adds it to 1 lot of this column. So we'll get 0 now in this entry here. And then for this entry down here, we'll get minus bc over a plus d. So we'll get d minus bc over a, and once again you can see that that's det over a, so this is equal to 1, 0, c over a, det over a. And we're doing the simple case where all of this is absolutely fine. So a isn't equal to 0 and det isn't equal to 0. Then we go further, so we're now going to take another matrix on the right here, and multiply it with our answer, so 1, 0, c over a, det over a, and we want to try and get closer to the identity. So what are we going to do? Well, we need to, for this first, and I've already made you see, this is why you shouldn't do it in this way, because you're just not used to doing it. So I almost then wanted to suddenly multiply it by something on the left, which would have been a disaster. So I'm supposed to be multiplying it by things on the right. So that was a good demonstration of what not to do, and why always do things on the left, just because that's what you're used to doing. So we need to multiply this again with something on the right, and we're trying to get closer to the identity matrix. So again, this thing in the first column here is going to determine what we get in the first column here. So what we put here is going to be multiplied by this, and what we put here is going to be multiplied by this column. So we want to subtract off from this first column a multiple of the second column. So we'll take 1/0 of the first column, so i.e. multiply it by nothing, keep it the same, and then we want to subtract off the correct amount here. So we need to subtract off c over det, lots of that second column, so minus c over det, because if we do that, this bit won't contribute anything, so we'll keep our 1 here, so we'll still have 1 there, but then minus c over det, the det will cancel and we'll get minus c over a, so we'll get c over a minus c over a, so we'll get 0 here. And then for our second column here, this column doesn't need any amounts of this column adding or subtracting off. We just need to multiply it through to make this entry here equal to 1. So we don't want any amounts of the first column, but we'd like to multiply through by a over det. And that should get us to the identity matrix. So therefore, our right inverse will be the combination of this matrix followed by this matrix. So let's just write those two out. So we've got 1 over a minus b over a, 0, 1, and then followed by 1, 0, minus c over det, a over det. And again, doing this, of course, relies upon the columns not being linearly dependent, which we're assured by the fact that our matrix has non-zero determinant. So let's multiply these two together. So we'll start with 1 over a times 1 is 1 over a, minus cancels with the minus, so we get plus b over bc over a det. So this is the complicated one again. 1 over a plus bc over a det. So you can remember from the last time how this simplifies. You get det over a det, and det of course is ad minus bc, so the bc's cancel, so we then end up with ad over a det. The a cancels, so we get d over det. So in fact I might just rub that out, and we'll get just right in there, oops, apologies, my pen is lagging, d over det. It doesn't like the rubber for some reason. So 1 over a times 0 minus ba over a det. The a's cancel, so we get minus b over det. 0 times 1 is 0, minus c over det there is that entry. And then 0 times 0, 1 times a over det, so we get a over det. And you can see that that is the same formula as we got trying to find the left inverse. So we've arrived at the same formula, congratulations. That demonstrates that either trying to find a left inverse or trying to find a right inverse by Gaussian elimination gives you the same answer, and it just involves doing it with row operations if you do it on the left, or with column operations on the right. But they're both Gaussian elimination techniques. It's just we're much more used to doing it with rows, so I would recommend that you do it with rows when you're trying to find the inverse of a matrix. And it is true, no matter how high up you go, that whether you do it on the right or the left, the answer you get is the same. So the final thing I want to discuss just briefly is just give you a glimpse of how this generalizes to higher order matrices. Now hopefully your mind's already whirring and you can already imagine how this generalizes to higher order matrices, and you'd be able to actually do this now for a 3x3 matrix. But just in case you need a little bit of a push, I'm going to give you that little bit of a push. So let's write out a 3x3 matrix, and by the way, we're going to go back to doing things on the left, not on the right, because otherwise I'll make a mistake. So A, B, C, D, E, F, G, H, I think I comes after H. I don't really know the alphabet that well, but hopefully that's correct. So let's think about how we would do Gaussian elimination to find its inverse. Let's assume it has non-zero determinant, because otherwise the rows aren't going to be linearly independent, and therefore Gaussian elimination at some point is going to break down. Let's also make the simplifying assumption that A is non-zero. If A is equal to 0, then you just go down and ask, is this one equal to 0? And if it's not equal to 0, then your first operation would be to bring it up into position 1, like I demonstrated previously. And then you'd continue on from there. But we'll take the simplifying assumption that A is not equal to 0. Now, one of the entries in the first column must be non-zero, because if they were all equal to 0, then it would be a singular matrix, because it would have a column of all zeros, and that makes the determinant 0. So one of them must be non-zero, and you'd move that one into the first position if A was equal to 0. But we'll assume A isn't equal to 0. So our first row operation matrix that we're going to put here is going to have, as the first thing, 1 over A, 0, 0. So remember, this is going to construct our first row in our new matrix. What we put in this row is going to construct the first row here. So all this is saying is I don't want any lots of the second or third rows. All I want to do is take the first row and multiply it by 1 over A. So that'll make the first entry 1. It'll make this entry B over A. It'll make this entry C over A. So we've got a little bit closer because we've got now 1 here. Remember, what we're aiming for is the 3x3 identity matrix, which is, whoops, not that. Rub that out quickly. It's this, 0, 0, 0, 0, 0, 0. So that's what we're aiming for. So we've got the 1 correct so far. Now let's try and get these bits here correct. So we want to get 0 here and 0 here. So if D is already 0, fantastic. All you do here is put 0 here, 1 here. And you'd keep that row exactly the same. But let's assume that D isn't equal to 0 and we have to do something more. So what we're going to do is take away the correct multiple of this row from this row to turn that entry into 0. So what will that be? We'll have 1 lot of that second row, and then we need to take away D over A lots of the first row, because when we multiply that by this, the A will cancel with the A here, and you'll then just get minus D in this first position, which will cancel with the D here to give us 0 there. So that's guaranteed to give us 0 here. What we're going to get then in the second two bits is going to be much more complicated. By the way, we don't want to fiddle around with the third row, so we will take 0 lots of the third row. So we're just 1 lot of the second row minus D over A lots of the first row. So what will we end up with here? We'll have E minus dB over A, and then, so that's minus dB over A comes from this, 1 times E comes from this, 0 times H comes from that, and then in this position we haven't really got room, annoyingly. I'll just extend these out. We will get F minus CD over A. So that'll be that entry. And then I want to do the same thing with the third row. So we want to get 0 here. So we'll take 1 lot of the third row. We won't fiddle around with the second row. So we'll take 0 lots of the second row. And then we're going to take away the correct amount of the first row to produce 0 there. So that'll be, we'll want minus G over A here. So that will give us a 0 there. And then we'll get H minus GB over A, and then we'll get I minus GC over A. And let me just check that I've done all of this correct. So here we took away D over A lots of the first row, so we got E minus DB over A, and then here we got F minus DC over A. So yeah, those are correct. I've just changed, my notation's not really consistent. It would have been nice if I'd written DC here rather than CD, but never mind. And then here we've taken one lot of the third row, and then we've taken away G over A lots of the first row. So we'll get minus GA over B and minus GC over A. Yep, so this is right. So we've made this bit correct now. What we'd then move on to doing is fixing up things further. So with our next matrix, we might like to try and make this entry equal to 1 and these two entries equal to 0. Now we could do that in separate stages. We could do a matrix that just makes this equal to 1, and then in the next matrix make these two things equal to 0, because then the amount of this line that we have to subtract off is a more simple multiple. Or we could try and do it all in one matrix. So I might try and do it all in one matrix, and this will be the last step that I show, because otherwise after it the notation is just going to get out of control. So I want to multiply by something on the left here, and then multiply my matrix 1, B over A, C over A, 0. Now let's just make those things easier. So A, by putting them over a common denominator, AE minus DB over A, AF minus CD over A, 0, AH minus GB over A, IA minus GC over A. There's our matrix. So now we want to try and multiply it by something else, and we're aiming to get this equal to 1 and these two things equal to 0. So let's start with row 1. So we'll take one lot of row 1, and then we're going to subtract off some multiple of row 2 from it, and that multiple is going to be A over this thing times B over A minus of that. So I think what we need to do is do minus B over AE minus DB lots of the second row. So I think if we subtract off that multiple of the second row, this cancels with this, and we get minus B over A. So we'll get plus B over A from the 1 here, and then minus B over A from this multiple of the second row. So that will give us a 0 in that entry. And then we'll want 0 lots of the third row. Now, of course, there's a complexity here, which we're not going to go into, because this is why I did it for 2x2 matrices rather than 3x3 matrices, because it's so much more complicated to do it in generality for 3x3 matrices, which is that we've just assumed that AE minus DB was not equal to 0 when we took 1 over it there. If it had equaled 0, that would mean the entry here was equal to 0, so we wouldn't have been able to do this. So what we would have had to do first is swap row 2 with row 3 with one of those sort of matrices that we've seen previously in the case of 2x2 matrices. So we would have been guaranteed that this entry down here couldn't equal 0, because if both of those were equal to 0, then this row here would be linearly dependent with this row here, and that would have implied that the initial matrices rows were also linearly dependent. So if this one was 0, it would be guaranteed that this one wasn't 0 if we'd started with a non-singular matrix. Therefore, we would be able to swap these two rows around and bring this one up into this position and this one down into that position, and then we'd have been able to do this. We'll make the simplifying assumption that this isn't equal to 0, and therefore we don't need to do that. So this is valid. So what's that going to produce? That's going to give us 1, 0, and then something hideous in that final position, which I'm probably not going to bother writing down because we're not going to take this calculation any further, but it would be C over A minus this thing here times this thing here. So something hideous. I'm just going to put d there. Then what we would want is we're trying to make this entry here equal to 1. So we'd want no lots of the first row, no lots of the third row, so we don't want them complicating things up, and we just want to multiply that second row through by A over AE minus DB. Now we've already made the simplifying assumption that AE minus DB isn't equal to 0, so that's a perfectly valid thing to do, and that will give us 0 in this position, 1 in this position, and then again something hideous that isn't quite so hideous, so I might actually write it out. So it will be AF minus CD over AE minus AB in that position. So all I've done is multiply that through with that. So this is looking good. We've nicely got those bits in. Yes, this is hideous. Yes, this is a bit hideous, but we're getting there. And then what we want to do is make this now equal to 0. If it already is 0, then fantastic. So if AH minus GB is equal to 0, then do nothing. Just put 0, 0, 1 here, because you've already got 0 and 0 there. So, and then something left over here that isn't 0. But if it's not equal to 0, then you need to take off some multiple of this row to make it 0. So we don't want any lots of the first row, we want one lot of the third row, and then we would want to subtract off AB, or AH rather, minus GB. I think that's what that says, AH, yep, AH minus GB, over AE minus DB. Lots of row 2. So this is getting utterly hideous, and I apologise for my poor handwriting. So if we subtract that off, so this thing multiplied by this, the AE minus DB will cancel here, and you'll end up with AH minus GB over A minus that. You'll get one lot of that from row 3. So minusing that amount of row 2 gives us the exact opposite things. You'll end up with 0 there. And then so we can now we've got 0, 0 in those two positions, and then in this position we'll end up with something absolutely hideous. We'll end up with this minus this times this, so I'm not going to bother writing that out, something hideous. Then what you'd finally do is you'd use this row to, sorry, my phone's doing something weird. You'd use this row to make these two things equal to 0. So you'd subtract off the correct multiples of this row from these two rows to make these entries equal to 0. And then you'd multiply it through by the correct amount to turn this into 1. And then eventually you'd get the identity matrix. And then you need to take all of your matrices that you've used on the left here, all of these row operation matrices, multiply them all together, and then you'd finally get the inverse for your matrix. Doing this in generality like this for general A, B, C, D, E, F, G, H, I, etc. is horrible. You end up with a horrible formula, which is why we're not doing it to completion. I'll make a mistake doing it anyway because the notation is going to become so messy. Doing it with actual numbers, you know, if you put numbers in here, especially if you've got nice numbers that have been picked specifically by someone setting the problem, is easier. So, because obviously you end up with nicer things, you can actually work out what these are at each stages and end up with a simpler looking matrix. So I hope that illustrates the idea of Gaussian elimination for these higher order matrices, and hopefully your mind can now run wild and do this. Obviously there are special cases where it would be more complicated and you'd have to think more and do different Gaussian elimination operations, such as if this had been equal to 0, where you'd have had to swap row 2 and 3 around. So I think with that we will finish there. Thank you for watching.